Krásné odpoledne, vážené dámy, vážení pánové. Já teda začnu česky. Rád bych vás přivítal na akci, která je pod záštitou fyzikálních čtvrtků. Vidím tady naše pravidelné návštěvníky, tak věřím, že tuto akci dobře znáte. Netradičně se scházíme ne v průběhu semestru, ale na konci zkouškového období. Nicméně já jsem velice rád, že jste tady přišli v takovém počtu. A dneska tady máme vzácné hosty ze společnosti Westinghouse, a konkrétně nového pana prezidenta české společnosti Westinghouse, pana Petra Březinu. A nám přišli povědět něco o možnostech nebo o stáži, kterou nabízí společnost vlastně Westinghouse ve Spojených státech amerických. Ale já předám slovo panu prezidentovi, který uvede naše dnešní hosty a zároveň asi řekne ještě trochu víc.
Dobrý den, děkuji. Chtěl bych vám poděkovat, že jste přišli. A my jsme požádali o tuhle prezentaci asi před měsícem a nakonec jsme to riskli, že to bude na konci zkouškového období, protože už ten čas se krátí. Já bych na úvod možná jenom představil Gorgemans, která vám tady řekne něco o AP1000, což je reaktor a technologie, kterou nabízíme teď na Dukovany, mimo jiné teda, a možná i jinde, jestli se všechno naskládá dobře. A její kolegyni Jing, Zhang, kteří připravili tuhle prezentaci pro vás. A k tomu vám ještě řekneme nějaké informace, které se týkají internship programu, který Westinghouse spustil letos podruhé. Poprvé to bylo v loni. A poprvé je to teda i v České republice z toho důvodu, že tady jako očekáváme, že tady budeme nějak působit. Jak víte, tak možná víte, tak my jsme vlastně v loňském roce dostali kontrakt v Polsku, ten už byl vlastně potvrzený polskou vládou a jsme teď účastníci v tendru tady v České republice, kde bude jasný dodavatel někdy koncem tohoto roku, možná začátkem příštího. Takže součástí toho je i, že tady v tomto regionu nějakým způsobem začínáme budovat do budoucna naše kapacity. V Evropě Westinghouse je přítomný, ale většinou je to v západní Evropě. Jsme v několika lokacích západní Evropy, v Německu, Belgii, ve Španělsku, ve Francii a začínáme budovat kapacity tady ve východní Evropě. Já jsem od tohoto týdne vlastně nový prezident, ale s Westinghousem už spolupracuju delší dobu, takže jsem byl při tom, jak se podávala ta první nabídka na konci listopadu a jsem rád, že teda ten fokus je teďka i na nás a že i studenti z ČVUT dostanou příležitost se do toho nějak zapojit. My teda jsme byli včera u pana rektora a domlouvali jsme se na tom, že bychom nějak spolupracovali i se školou průběžně, nejenom tady na tomhle programu, ale i jinak, možná nějaké speciální přednášky nebo něco takového. To se ještě uvidí. V každém případě Westinghouse si uvědomuje, že tady v Česku jsou kapacity, které dovolují vlastně ten rozvoj té jaderné energetiky, že jsme jedna z mála zemí na světě, která si v minulosti jaderné bloky postavila sama, i když na základě nějaké licence ze zahraničí, ale doufejme, že i do budoucna budeme maximálně soběstační a že se tady vybuduje nějaká další generace, vlastně, která bude schopná na těch nových blocích nejenom participovat na té výstavbě, ale i dál na tom provozu. Ty bloky fungují, že dneska je to 60 let je běžný a do budoucna se počítá i 80 let, že budou mít životnost. Takže je to partnerství na 100 let, když to řeknu. Ještě pak decommissioning 20 let. Takže já bych předal slovo Julie. Já bych jenom možná jednu věc, ona vám potom řekne o tom programu. Jo? A bude to velice rychlý, protože my už jsme, jak jsem říkal, my jsme to chtěli dělat v lednu a bude ten program bude v létě, v srpnu. A do té doby je potřeba udělat spoustu kroků, bude tam nějaký výběr, nějaká selekce. Děláme to jenom tady na ČVUT a děláme to na Západočeské univerzitě, nikde jinde. Vlastně jenom s váma a s Západočeskou univerzitou jsme dohodnuti na tom, že prostě odsud ty studenti, kteří budou mít zájem, jsou tam nějaké podmínky, samozřejmě nějaké CVčko a výsledky studia, ale bude tam i nějaká esej. A ta esej docela dost souvisí s tou přednáškou, která tady dneska bude. A potom, až budete se zamýšlet, jestli do toho půjdete, tak jenom, abyste si dali pozor na to, co je vlastně otázka, co je vlastně to zadání. A abyste si dali pozor na to, jak vlastně se vyjadřujete, protože to bude 80% toho nějakého vyhodnocení. Nebude ani tak úplně důležitý, samozřejmě bude, aby to mělo hlavu a patu, jako co je uvnitř, že nikdo neočekává, že jste jaderní inženýři, ale protože vlastně ti technici taky jako hodně komunikují navenek, takže chceme, aby ty lidi prostě byli schopni se nějak vyjadřovat. Jo, takže vám děkuji, že jste přišli. Já předám slovo Julie.
Okay.
A ona, you have your own microphone. Okay.
Yes.
Takže děkuji.
Okay, thank you. So in the next 15 minutes, my colleague Jing and I, we will try to explain to you how, for the plant that we hope to build in Czech Republic, but that we've already built in China and are currently completing in the United States, we went with a very different approach to nuclear safety compared to all the other plants that are currently operating in the world. So in order to do this, it's important to understand what came before. So Westinghouse has always been an historical actor of the development of nuclear power, so the use of nuclear to produce electricity. We were part of the companies that had initially been selected to participate to the development of nuclear power in the United States. Through that role, we were actually the organization who designed the first pressurized water reactor, which are the most common types of reactors in the world. And our technology is actually at the basis of about 50% of the nuclear power plants that are operating today in the world. So we started building commercial power reactors in the late 50s. In the 60s, 70s, we had lots of customers knocking at the door, wanted this great asset in order to produce great amount of electricity. But obviously that was a very moving environment, and what happened as we were executing projects after project, some changes were coming through. The regulatory environment was being developed pretty much as we were going. So we had lots of issues with our projects that were coming longer and longer. It was taking us longer and longer to build the nuclear power plant. The cost was going up. And so after a first wave, which was significant, of about 100 of nuclear power plants, basically the order stopped for us. It stopped for us in the United States. It stopped for us mostly in Europe, which was the market where we were active outside of the United States. And so when you don't have any new orders on your book, well, you have two choices. You either close the door and go away, or you try to think about what do you need to do differently in order to unlock the market again. And this is really what is the basis of AP1000. So each time we design a nuclear power plant, a new concept, our main and foremost goal is always to be safer than the previous generation. That is something that is a given in the nuclear industry. Safety is the first priority and the most important one. However, we also thought about, okay, what is driving cost and duration in our projects? Well, one of the things that drives cost, it's how much things we need to put in the plant, how much cables we need to pull between the equipment and the sources of, between the INC cabinets and the sources of power, how much piping we need to install. So the first thing that we decided, okay, is we need to reduce the number of things we have in our plant. By definition, the best equipment is the one that's never going to fail when you operate, that is not going to cost you money to buy at the beginning, that you're not going to take time to install, that you're also not going to produce as a waste at the end of the plant life. It's the equipment you don't have. It's the cubic meter of concrete you do not have in your plant. So the second objective of AP1000, after being safer, was to be simpler. And that simplification, we applied it to everything. We applied it to normal operation. All the systems that support the plant when it's producing electricity, we took a hard look at it. How could we make it simpler? How could we eliminate functions in order to simplify equipment and minimize the footprint of the plant? But we also applied it to the safety. And this is why we went differently than all the currently operating plants. Why did we go for a passive safety approach in the AP1000? It's because if you want to be simpler and safer, that was the only route that was available to us. Another source of the cost, and that's why we have another objective in the AP1000 design, was customization. I see one of the students has a bright orange t-shirt. His neighbor has a sweater that is black. Well, everyone has their favorite colors, their favorite way of doing things, and it's great. But me, if each customer, when we are only building a few plants a year, always come with a different sets of requirements, it's always increasing cost, because each time I need to design something specifically for my customer, I need to go potentially to new suppliers for first-of-a-kind equipment, and all this is driving cost. So we were not the only ones realizing that this was actually an opportunity for industry, and the utilities themselves, so the companies that operate nuclear power plants, got together. There was one effort in the US, but there was also one effort between European utilities where they decided, okay, we're going to get together and agree on what are our requirements for plant designers, so that the plant designer could then design one plant and sell it to multiple customers. That was the putting in common their requirements. And so if there is anything you need to remember today about AP1000, that's the three words in green on the slide. Safer, simple, and standard. I want to be able to build the same plant no matter who's my customer, what's my country, what's the site.
I'd like to spend a few minutes to provide you kind of short introduction for the global AP1000 plant design before we go into the more detailed safety passive system topic. So just as a short background, what we talked as AP1000 new plant standard plant design, you have basically the biggest building is obviously the turbine building, which is not which is outside of what we call nuclear island. So the most important part, which contains the reactor and all the primary system, is inside of the shell building. Inside of the containment, which is surrounded by the auxiliary building. You see the tallest cylinder building is the shell building, surrounded by the auxiliary building where we have located the fuel or the fuel handling area, plus electrical, mechanical, or the auxiliary system stuff. And then the shell building plus the auxiliary building, that's what we call the nuclear island. And then you have the other annex building, red waste building, and obviously the diesel generator building, which provide the on-site power. So as a very basic number of thermal output you have from the primary system, the AP1000 design. From the primary system we have about 3,450 megawatts at thermal output. And in terms of electrical power from the whole plant, we are between, it varies depending on the different site, and it varies between 1,100 and 1,200. So that's the basic ballpark of where we are. Then talking about the primary loop, we are having a design with 2 loops. That means 2 steam generators which are linked with the hot legs and the cold legs to the reactor vessel. So the primary system is operated at about 155 bar pressure, and the normal operating temperature is above about 300 degrees. To provide you a kind of basic idea on that. So that was the big background of the essential system. Then today's topic is talk about the safety, which is our essential topic for the nuclear industry. So AP1000, we always said that AP1000 design is different in terms of safety system design compared with the traditional ones. So as my colleague Julie explained, we try to, when nuclear industry started to be aware of the problem during years, the problem of doing very heavy safety system and becoming more and more cost consuming and more time consuming in construction, in all kind of the quality inspection related with nuclear safety code and standard. So we try to make things simple and safe at the same time, of course. As all the traditional design, we do keep all the part of active, which is called active defense in the systems. That means they do help in normal operation. All the active system do help a lot on to provide reliable support for all kind of normal operation. And then we do have the on-site, for example, the on-site diesel generator power, which can provide kind of redundancy for the equipment that are all part of, let's say, traditional active system, which do help. And what is really different here for AP1000 design is all that kind of active system, we don't want them to be the part of a safety system. And the reason is two hands. On one hand, we don't want them to be classified as safety system, which means if they are not nuclear safety, we just use from the conventional industry, we just work with the conventional code and standard with associated inspection, fabrication, installation rules. So that's not going to be much more expensive than the conventional industry. That's on one side. The other side, which is most important, is that we don't want to be really dependent on on-site power, on-site AC power, DC power, nor be really dependent on operators' actions. So that comes up with what we call the passive safety-related system. So, in summary, the passive safety relief system is operating in front of a basic accident. We are just operating without active system, for example, without active pumps, without the need of on-site diesel generator power, for example, and we are not dependent on operator action, things like that. So after the Fukushima event, we are really the whole world, the nuclear industry was right before the Fukushima event. We were already aware of that kind of event when it happened. We are really have the first 3 days without on-site power. That was widely aware within the industry, nuclear industry. But the Fukushima event was just bringing this kind of attention to the whole world. So that's kind of approved that's kind of approved where you can see the real advantage of the passive safety system, where we are really not dependent on that much on-site diesel power, and neither on operator action or any of the active system. So so with that we are coming back what we call the passive system, the passive safety related system is a kind of design philosophy which is simple and safe. So that's kind of summary. It sounds like a little bit magical to be too magical to believe. So what in reality, what can we do to really achieve them? So that comes up our safety functions, which is required by our passive safety systems. There are a lot of them. We can't really list them in one slide. So basically, you have core cooling safety function for core cooling, for containment cooling, for example, the spent fuel cooling, and for example, you will need the chemical and volume control for fluid system, and you will need fire protection. For example, in the event of design basis analysis, and you will need the main control room to have the minimum ability. For example, a lot of them. But for all of them, we can continue talking days and years. But mainly today's presentation, we are going to be focused on the core cooling part.
Okay.
Yeah.
So. What we have as safety functions in a nuclear power plant, it's always the same goal. What we want to protect is protect the different barriers that prevent the spread of radioactivity from the core, where the nuclear fuel is located, to the outside, to protect the environment and the public which is living there. So the first barrier that we have is the fuel cladding. So without going into too much details, the actual nuclear material in a pressurized water reactor is oxide uranium, enriched up to 5%. It's in small cylinders, and those cylinders, they are first in a rod, and that rod, that's the first barrier. That's actually something we're going to count upon to keep it there, keep it inside the fuel itself, but obviously the fission products, which are what is bad and what is creating doses to people. The first The second barrier, and I'm going to go back a few slides. So all the fuel and the core is located in the reactor pressure vessel. Our primary system, so the vessel itself and the steam generators and so on, that works in a closed loop arrangement, okay? So water just circulates to take the heat away from the core and bring it to the big heat exchangers that we call the steam generators, where we can heat up a nervous system and produce steam that goes to the turbine. Because that works in a closed loop, that is another barrier that we want to protect, okay? And finally, if I go back here, our entire primary system in a pressurized water reactor is located inside containment. The name of that building kind of indicates what it does because it contains. That's actually its only purpose, is to ensure radioactivity remains contained within that building. So all the safety functions that we have in nuclear power plants, they're there to protect those three things. So what could challenge them? Well, unfortunately, the nuclear fission reaction, we cannot stop it instantaneously. So even when we shut down the reactor, we're still going to have heat being produced in the reactor. So we want to, one, effectively shut it down, which means we have rod control assembly, which are materials that do like to eat neutrons, to absorb neutrons, to try and prevent them from causing another fission reaction. We also have boron that we dilute in the water, which also likes to eat boron and absorb boron and prevent another fission reaction. Core cooling, it's preventing more fission reaction from happening, but it's also taking the heat away from the ones that are still happening, no matter how good I am at shutting down the reactor. And that is done by having a system that can still take the heat away from the core and put it somewhere else. We don't want to leave it in the reactor coolant system because we also want to protect the reactor coolant system. So we need to be able to take it from the core and transfer it somewhere. That somewhere is going to be the containment atmosphere. That's what we're going to see. And so we also need to take it away from the containment because we also want to protect the containment from overheating. Fire protection, as the name indicates, well, as anywhere, a fire could one day happen, and we need to be sure that our plant is safe in case of a fire. As I mentioned, we have decay heat. That decay heat is going to last forever. It's an exponential curve, so we have less and less as time goes by. But what we're going to do once the fuel is done with producing electricity, we're going to store it in another place of the plant, which is called the spent fuel pool, and we also need to cool that. Those are just examples of safety functions. And so all those in our plant, we had to define a way to do it passively. And so that meant a lot of testing and research to define those ways. But so to go back more onto core cooling, so we have a dedicated system that we call the passive core cooling system. I know we're not very original with our names, but the main functions of that system is to do exactly what I said. So first thing, we want to bring borated water into the primary system to ensure we are effectively shutting down the fission reaction in the core.
So everybody knows what is the core? You know?
Okay. Yeah. By the way, nothing prevents, if you really can't follow, please raise your hand and I'll try to explain any term that I'm using. We also want to provide safety injection. So safety injection is something we only going to need for some accident. But among all the possible scenarios that we postulate could happen in a nuclear reactor, there is the one where we have a sudden rupture of a piping within the primary system, which means we're losing all the water that we were counting on to cool the reactor and to provide to shut down the reaction. And so to do this, we have additional sources of water that are there just for that, to always ensure, even if we have basically a big rupture of a pipe in the primary system, that we maintain the core in the right condition. We also need to remove the heat that continues to be produced. That's what we call the decay heat. So we're going to have a system to do that. And we're also going to control the pH of the water within containment. So that's a bit more technical, so I apologize in advance. But depending on the pH of the containment water, so when we have a break, the water which is escaping from the reactor coolant system, it basically goes at the bottom of containment. It's the same thing at your house. If whether you have a pipe that bursts at your house, I don't wish that to you, but the water is just going to flow down until it gets to your basement. And then it's going to stay there until you get a pump to get it out. Well, it's basically the same in AP1000. Every water that we lose through a pipe break, it's just going to go at the bottom of containment. Within that water, there's a number of radionuclides, which is what is radioactive, what can create dose for people, that will potentially stay trapped in the water versus being in the atmosphere where it could potentially escape. And the pH of that water is actually influencing how much of those bad radionuclides stay in the water. So that's why we also need to take care of that. Those are all the functions, but today I'm going to focus on a few just to exemplify what is a passive safety system. And so since I was encouraged to use the board, I'm going to use the board. Okay. So first of all, there's many different classes of passive safety systems. The one that we're working with in AP1000 is a system which is on standby during normal operation. It has no function during normal operation and requires a one-time valve alignment in order to actuate, in order to start functioning in case of an emergency. An emergency is any accident that my plant could see happening. And I want only to use physical phenomena in order to push fluid. I don't want to have a pump. I don't want to have a fan that could potentially cool down something. I only want to use passive processes and natural phenomena like natural circulation, gravity, among others. And so two of the systems I'm going to describe to you in a second, they both work on the same principle, which is natural circulation. And in the two cases, what we're going to try to create is a column of hot water and make it loop, create a loop with a column of cold water. And during normal operation, we will have a valve of a kind. This is an air-operated valve, but it doesn't have to be this, which is closed during normal operation. Okay? So how do we keep a hot column of water versus a cold column of water and have them touch each other? So that's a very good question. So what we have in the nuclear power plant, it's a very good heating system, which is called the core. Okay? The core produces lots of power. As Jing mentioned, our reactor coolant system operates above 300 degrees. This is quite hot. I mentioned that we are all located inside our containment. I'm not a very good drawer, so I hope that's actually okay. Oops. And our containment during normal operation, it is, let's say, around 30 degrees C. So we have something here, which is 300. This pipe, I'm going to firmly insulate. I'm going to put lots of thermal insulation around it, okay, so that it stays hot inside because it's in contact with the very hot primary system. This pipe, I'm not going to insulate it. I'm going to actually leave it very free to exchange any heat that enters in that pipe with the containment air, which is just next to it, okay? And so when I have an emergency, I'm going to design my system so that this valve opens, and only the difference on density between the two columns of water is going to induce a natural circulation of the water. And so water will basically, the heavier cold water will be pushed in the system. Okay? So First thing that I said we need is borated water. We always need borated water, no matter what is the accident, because even though we use those solid control rods to shut down the reactor initially, there are phenomena that's going to increase the reactivity of the core in the longer term, and I need to provide additional anti-reactivity. So anti-reactivity is basically providing more substances that can absorb neutrons, like boron. And so we have tanks in the plant that are dedicated to that. We have 2 of them. They're shown in blue over here. And that's all that they contain. They contain cold, borated water. Okay? The top of the tank, it's connected by a balance line that is connected to the primary system, to one of the cold legs, and which is firmly insulated. Because I know the name can fool you, but the cold leg is still at 300 degrees during normal operation. It's just colder than the hot leg. So this pipe is going to remain very hot during normal operation. The tank itself and its outlet line is not firmly insulated. So it's actually staying cool during normal operation. And any flow in the loop that is created by those 2 piping is prevented by the 2 parallel valves that we have, which are both closed during normal operation. So if I have an emergency, we have a dedicated instrumentation and control system that monitors key parameters of the core, and if they detect anything going outside the acceptable range of operation, it will activate those 2 valves. And those 2 valves, once they are opened, we have again that hot column of water, that cold column of water, and hence the circulation, and that circulation will bring the cold borated water inside the reactor coolant system to be diluted with the rest of the water that we have there. Jing mentioned we don't like needing power at all. An instrumentation and control system, it still requires power to function. Compared to a system that would do the same function by using a pump to inject into a 155 bars pressurized system, we're using much less electricity than that solution. But we still use a bit. We use a bit to have our control system monitoring the core and to open the valve. So with AP1000, we even went further. What we did is we designed the valves that needs to open so that they fail if I lose electricity at the plant. So those valves, we need actually compressed air to maintain them closed. To keep the pressure in our compressed air system, we need electricity. So if I lose electricity, those valves will always open. That's what we call fail-safe type of valves, because in case of a failure, the valve automatically switches to the position which is safe for the plant. Very similarly, the way we're going to remove the heat, which continues to be produced inside the reactor, is going to function also with a similar principle. Instead of having a tank of cold water, borated water, we're going to put a heat exchanger. And that heat exchanger, you can see it here. It's a C-shaped bundle of tubes through which the primary water is going to flow. And that heat exchanger is located in a big tank of cold water inside containment. So that tank has quite a large inventory of water. So it will slowly heat up as heat is being transferred from the core into the water in the tank located here inside containment. Even though it has lots of water, it's still going to start boiling eventually. And so we designed the tank so that it is actually open to the containment. It's not a closed tank. And so any steam which is created in the tank is going to start rising into our containment, getting on top of the core. And that is how we remove heat from the core, from the reactor coolant system, and we dump it into the containment atmosphere. So of course, the next question is, how do we remove heat from containment? Because so far, the only thing that I've done is take it from here and put it here in the form of steam. Now, that containment, I also rely on him to contain the radioactivity. So it's a thick metallic containment vessel that we use in AP1000. It's able to take a significant rise in pressure and in temperature, but eventually you will get to its limit. So you need a way to remove the heat that you are currently storing as steam on top of containment. And the way we're going to do this is actually by leveraging the fact that we have a metallic containment vessel. Because metal is good for one thing, heat transfer. It's a good heat conductor. So what we're going to do is spray the containment with water. So we have a dedicated tank, which is located outside of the containment, on top of the containment, within the structure that we call the shell building, which is the building you see here on the outside. And we're going to basically let the water rain on the outside surface of the containment. As it flows along the containment vessel, it takes some of the heat away, from the steam. The steam is going to condense. Some of it may rain into our containment cell, but most of it will be collected alongside the inside surface of the containment, where we have a gutter system, so just like you have a gutter systems on your roof, for example, and brought back to our in-containment refueling water storage tank, which is the big tank that we use as a heat sink for the heat exchanger that we're using to remove the core. So basically, everything which is inside containment stays inside containment. I'm taking the heat away from the core, creating steam from that tank. Steam is rising in the containment atmosphere, where it gets cooled, condensed, collected in the gutter system, and brought back. So basically, we're working in closed loop again. Okay? So when we say we have, Jing mentioned earlier, we have 72 hours of mitigation in case of an accident without any operator action, actually without any instrumentation and control action either, because we always use fail-safe valves for all those systems. That's because that tank, after 72 hours, the one which is on top of containment, will be empty. And so, after 72 hours, what do we do? So, we have placed dedicated equipment in the plant. Those are no longer passive, purely passive. Inside the containment, everything I had described continues. But how are we going to continue bringing water on top of the containment? For that, we're going to use a very small pump and a very small diesel in order to continue cooling the containment and hence maintaining the plant safe. And so we have a tank, dedicated tank in the yard, so close to the reactor building for 4 additional days of water. The diesel that we're going to use is actually pretty small. That's about my height. It's actually quite light in weight, which means that if for some reason the equipment that I have at my site is not available, I can bring easily another one by truck, by helicopter if needed. And this is very important when we think about Fukushima, because if you are one day faced with an event which is so bad that it has taken everything at your site, when nuclear power plants are designed themselves to be extremely robust against external events, well, most likely everything else around you is also no longer there to help you. So the capability of bringing support by road is not going to be reestablished for some time. So having an equipment which is light enough so that you can actually helicopter transfer it to your site is a significant advantage in terms of resilience against extreme events. And so, to give you an idea about how we have improved the safety with AP1000, a typical nuclear power plant, the requirement which was applied to it before Fukushima was to be able to lose all electrical sources for 4 hours. Most plants were doing a bit better, 4 to 8 hours. After Fukushima, the number of them did modifications in order to improve that. But with AP1000, we have 7 days without doing anything. And obviously, we designed AP1000 before Fukushima. So that's nice, but if it's not surviving the actual reason why you have an event, the earthquake or the tsunami, that's not really helping you. If your equipment is not designed to sustain a seismic event, then it's not helping you. So in AP1000, we are designed for a significantly seismic event already. And what we have done is we've looked at what if the event is even bigger than what we're designing the plant for. And we have demonstrated that we have significant margin beyond what we had assumed in the design. For the flooding, that's a bit of a different story. All nuclear power plants, they're designed to stay dry. Just like everything, your phone, your TV, if you ever have a flood at your home, it's not going to like it because electronic equipment and electrical equipment are not exactly friendly with water. So nuclear power plants, we always place them in terms of altitude, elevation, so that normally it should not be affected by the higher flood possible. Now, what Fukushima demonstrated is that sometimes we get it wrong. Again, with AP1000, that is not a concern in terms of nuclear safety. Why? Because if I do get indeed flooded, and all my plant is flooded, because all my safety systems are located inside containment, as you can see here, everything is in there. That containment is a thick metallic containment vessel, which can take the wave, so that's not going to be impacted. It's closed, so the water is not going to get in. And because I've designed my system to fail safe, if I lose electricity at the site, they will still actuate. They will still maintain the plant safe. They will cool the core and cool the containment. And this is why we really believe that AP1000 has provided significant advancements in terms of nuclear safety. One, by designing it to self-actuate. If I lose everything, all my INC system, all my electrical support systems, I will still have core cooling and containment cooling, and my fuel, my radioactivity will be contained. It is self-sufficient. So we compare to an active plant, the amount of grace period, how long we can survive to an event on our own without doing anything is extremely long, those 7 days that I was mentioning. And finally, it is self-protected. The biggest advantages of passive safety systems versus active safety systems is that they are so compact. Not the system itself, but the fact that we don't have all that network of support systems that active systems need. Because they're very compact, we can put it all inside containment, where it's protected against external hazards. The containment itself, which is here, which is already, as I said, a thick metallic containment vessel, is further protected by a building that we call the shield building, and as the name indicates, its main function is to shield. It shields the containment from any kind of external aggression that it could see. External aggression in the sense of a tornado missile, but it can also be man-made hazards, as we call that, in a very nice fashion, like an aircraft crash or any kind of attack beyond natural hazards. Of course, that is if you believe me that that works, everything that I've said so far. And so usually the first question I get when I give a presentation on passive safety is, how do you know it's going to work? Well, we know it's going to work because we have tested it heavily and analyzed it significantly. So the next few slides, what I'm going to do is walk you through how we have developed and demonstrated our passive safety systems. So when you do something which is new, and I'm sure that as university students you know that problem quite well, the first thing that you ask yourself is, how am I going to model this? How am I going to prove that I have something that can calculate in advance how it's going to work? And so to do this, to develop the computer codes that we're going to use to do our safety demonstration, the first thing that we need to understand is, what do we know? And so the first exercise, as we design a new plant based on passive safety systems, we're going to do something which has a bit of a terrible name called phenomena identification and ranking table. So we design a sketch of an idea of how we think a system could work, and then we ask ourselves, what are all the physical phenomena at play? Obviously, if I'm looking at this, the main one is natural circulation. There are going to be other physical phenomena that come into play. So we go back to Physics 101. We put them all down, and we do this through an expert elicitation exercise, which means we basically take a bunch of experts in the room like today, and we ask them, okay, tell me everything that is influencing how my system works. And so once we have done that, we, again, based on an expert opinion, not one, but a group, we ask, okay, how important do we believe the phenomena to be in the working of the system? Again, going back at the board example, natural circulation would be the most important one. Okay? But there will be other ones that we will define in importance. And then the last question that we ask ourselves, and for that we need hard-proof references, is how much do we know? What test experiments may have already been carried out that applies to our case? How similar may it be from phenomena that were already measured at nuclear power plants? And based on that, how important it is and how much I know, I can define my testing plan. And so what we're going to do is, for each area that is of medium or high importance and for which I feel I do not know enough, I'm going to do a test. I'm going to do a test to define a heat transfer correlation. I'm going to do a test to verify that indeed I succeed in predicting how much how much flow rate I'm going to have in the loop based on the resistance in the piping. And so first, you do testing which is only on one specific thing. So for example, this is actually the borated tank that I presented earlier. And we wanted to see what happens is, instead of having hot water here, you get steam. How does that influence the natural circulation? The reason why we ask ourselves is because if I start having a big pipe break here, that's not going to be water in that line anymore. That's going to be steam. And so I need to understand how it works. I mentioned we were going to do some experiments to look at heat transfer correlation. A passive safety system, one of the characteristics, it's actually that it operates with a very low flow rate compared to an active system. Since we are only relying on physical phenomena to push fluid, we don't have some equipment bringing work into the system, so we have very low flow rate. And so when we looked at heat exchangers, even though the heat exchanger that we're using to remove decay heat is very similar to a lot of the technology we are already using in previous generations of plant, we were never operating it with such low flow rate. So we did experiments to define what is the heat transfer correlation that actually applies to my case, like validate our choice of theoretical heat transfer correlation. Once you have all that, you can develop a model. You use your model to predict how it's going to behave on a test facility. So what you see in the last picture, it's SPES 2. It was a test facility in Italy that represented all the passive safety systems of an AP1000 with the correct height. We took our code, predicted how the system would behave in case of an accident, and then we ran simulation on the test facility and compared the results. If our code was predicting correctly what was happening on the test facility, that means we have correctly represented the phenomena at play in our passive safety systems. Once we have validated that our codes were okay, that's when we can do the safety analysis. We do single failure, multiple failure, all kinds of crazy scenarios. We also look at how compatible our design is between the operating procedures that the operator may be, some actions that the operator may be taken, as well as the functioning of the passive safety systems. We went through that exercise during the design of the plant, but we were not the only one. Another thing that characterized the nuclear industry is that we're a heavily regulated industry, which means we have regulators looking at everything that we do. And so as part of the design of AP1000, we applied for reviews by regulators. The first one was in the US, the Nuclear Regulatory Commission. They went through the same exercise as us, which means they went through thinking about what testing they should be doing, obtain the results, develop their codes, predicting the behavior of the plant, and confirming the results of our safety analysis. A few years later, when we were in the United Kingdom, we also applied for a review by the regulator. They didn't have the time to do their own testing. That was a shorter program. But they took our testing and developed their own codes to validate our safety analysis. So once you're at that stage, you're designed and you're licensed. And what you know is that the systems, as you've put them on paper, they will maintain the plant safe. But once you build an AP1000, as every time you build a nuclear power plant, there is also an important step, which is verifying that what you have built is what you had designed. Because obviously, if people don't build what you said they should build, then there could potentially be an issue for nuclear safety. And so we have what we call the commissioning program, an initial test program that will again verify that it's not just my paper design that meets my safety analysis requirements, it's also my actual plant. That the fundamental assumptions I've made in the safety analysis remain verified by the actual plant. And so yes, we can test how much flow rate I have in a natural circulation loop. We can test how much heat is being transferred by that heat exchangers, for example. So we will do it initially before the plant is authorized to operate, and we will repeat those tests when the plant operates every now and then. We have different frequencies for different tests, just to check that there isn't any kind of degradation that could, again, impair the operation of the passive safety systems and take us out of our authorized domain of operation. And so, in conclusion, what we've tried to convey to you, AP1000 really has a different approach to safety compared to all other operating plants. And that is that we've kept the active systems, but we've simplified them. They are non-safety related, which means we do not rely on them to maintain the plant safe. And we've added those, that robust line of defense made up of the passive safety system. Compared to any other plant, AP1000 has a unique response, an unparalleled response to an extreme event, because we are self-actuating. Our passive safety systems will always actuate. We're self-sufficient. We provide extended grace period, extended mitigation time of an event without operator action, without any need for any action. And we are self-contained. Because of the compact footprint of the safety systems, we can put them all where they're protected against a flood, against a seismic event, against any external hazards. And finally, you don't have to take my word on it, because we are testing the systems. We did it when we designed them. We continue doing it each time we are starting up a reactor, and our customers, the company that actually operates the plants, will continue testing the plants through the plant life. So that concludes the lecture part. And now we have, yes?
I think what is important for understanding is that whatever is outside in the active system and it's connected to inside the containment, there are different requirements for the suppliers and for quality, which we don't have on the passive system. So
Correct.
it's much more expensive, and of course, you can see the complexity. It's different. Right?
Yep. So, last topic for today, the internship program. So we are organizing this year, this summer, an internship program. So basically, we would like to invite some of the students from this university to come and spend 6 weeks with us in the United States at our headquarters position. So what is an internship? It means you would be embedded into one of our engineering groups that works on AP1000, but also on other new designs or on support to the operating fleet. And you will be doing engineering tasks as you would if you were a young engineer joining us. So you can see the dates here in terms of specific schedule. Our offices are located outside of Pittsburgh. So I know you've never heard of Cranberry Woods, but think Pittsburgh, Pennsylvania. The conditions, you have to be a student because this is our target. We prefer that our students have some experience already and have gone through some classes. So last year, a bachelor's degree or master's degree students is what we're looking for. We're asking you to be an EU citizen. It's not that we have anything against non-EU citizens, but in the nuclear, we have to request authorization to share nuclear information with different nationalities, and EU is already pre-approved if you want, so it simplifies the process. And we ask that you are fluent in Czech and English because that's the language in which you're going to be working. So fluent doesn't mean that I need you to be able to read Shakespeare in the original text. It means that you are able to understand me today and that we can have a conversation when needed. So a B2 type level, I would say, is sufficient. Czech, because I think Peter mentioned it in Czech before giving me the floor, that one of the reasons why we are doing this internship program is that we need to grow and that we are looking for engineers that will eventually join us in Czech Republic. And so, no, it's not good.
But this is also our contribution to the nuclear industry in Czech.
Correct. And to apply, so you have 3 weeks from now, the deadline, which is March 9. We would need a CV from you to understand a bit your background and what you've done so far, your academic record, so the list of classes and the grades that you have obtained, and a 1,500-word essay on the benefits of passive safety approaches for nuclear safety. So, what do we expect with the essay? We expect basically you to give us a text which is logically organized, which has references, which has paragraphs, and that talks about the benefits of passive safety systems. Okay? So we will be providing a leaflet to your professors to share among you with where those details are repeated, as well as the application link, so that you know how to apply. Any questions on the technical side or the non-technical side, aka the internship? Yes?
What about master's students that are currently in the last year of their masters, and during the summer they will already be engineers?
So, as long as you are, if you've been enrolled in 2023 in university, you can apply. No, so you will, if you don't get the, so I do have business cards that I can provide to whoever is interested in our internship program in case there is any kind of communication issue, but the link is not, we are only working with your university and another university in Czech Republic. Because of that, the application link, it's not something you can find if I'm not giving it to you.
And you will get it.
Yes.
We will will send detailed information
Yes.
with the links to the school, and they should distribute to people which are interested. And yeah, the deadline is quite short. It's 3 weeks, in fact. So, but maybe we can also say that example of last year in Poland. So we did it first time last year in Poland. So it was quite successful. We do it this year in Poland, Ukraine, and Czech Republic. So we expect that there should not be any problems for you to enroll. The time is short because there is a process behind.
So yeah.
So after the application, so there will be selection.
After the applications, the best applications will be invited for an interview, and then based on the interview, we will make our final selection. So that takes a bit of time after March 9, but the main driver for that application date is you need a US visa in order for you to be employed in the US by us. And that visa process is the major step in terms of time. It takes few months to get to do it. So July is not that far away.
And what is important that everything is paid by?
Yes, that's a very good clarification. So one thing which is very important for us is that anyone interested can apply. So we are taking care of all the costs linked to the application for the visa, the plane ticket to the US. We'll even ask you if you want to spend a bit more time in the US before and after so that we book your flight tickets for when you want. We'll pay the accommodation in the US. We are paying you during the internship. And we're paying you weekly and in advance so that from the start you have a bit of money to ensure that you can cover your expenses, like food or entertainment or whatever you want to do. We'll also organize technical visits for you in either our facilities or facilities of partners that we have. We'll invite you to some cultural or sports events. Like in the summer, it's full baseball season. So if you like baseball, you will see some baseball, that's for sure. And you will also be invited to technical presentations in addition to the normal work so that you can get to know not just the department where you work at Westinghouse, but the other departments as well, so that you can get the full picture of our activities over the summer. Correct. We are not looking for just nuclear engineers. Nuclear engineers welcome, but in nuclear power plants, we employ more or less any engineering discipline in order to design it and to build it. So there is no restriction. Mechanical, civil, IT, electrical, electrotechnical. I'm not going to list them all, but you get the picture that as long as you have a strong technical background, you're an engineering student, we have something for you in our departments.